The broadcast is now starting. All attendees are in listen-only mode.
So good morning or good afternoon, everyone. Good evening, depending where you are. Thank you for joining for this session 1 of the virtual WSTS series. This one will be on 5G and smart cities. My name is Stefano Ruffini, and I will be your moderator today. I will get help from Lee Cossart from Microchip as a vice chair during this session today. So this virtual WSTS webinar series is being held in place of the annual face-to-face WSTS. And for those who are new to WSTS, this is a conference with a quite long history. Next year it will be 30 years. That's incredible. This was founded and still chaired by Mark Weiss. And for the few who do not know Mark, you will get to know him on the third session of this event in a couple of weeks. It will be the session on timing security, resilience, and GNSS issues. In fact, as you can see, the conference is arranged over a series of 3 sessions, and the next 2 will be held in the next couple of weeks, the same day, same time, so easy to remember. A couple of logistic information before we start. So the slides and the recording of today's presentations will be mailed to all the registered attendees. There will be a couple of question and answer sessions during this webinar. So please submit questions using the question tab on the control panel that is located on the right side of your screen. And I would like to say that we are very pleased to share that there is an incredible good number of registrants from around the globe that will attend today. So I'm really excited for today. And before we start, I would also like to thank our speakers, as well as Microchip Technology for sponsoring the webinar of today. So I would like to just spend a few words in the next slide as an introduction to the session today. So this is about 5G smart cities. What does it mean? I think it's a really good time to speak about that because 5G is really now becoming a reality. It's more than 1 year that is being deployed in the world. There are several networks already in operation, operating 5G. From a standardization point of view, there are new releases addressing enhancement to the standard that are being released by 3GPP and will continue to be released in the coming years, adding more and more functionalities to the standard. One aspect that I think is particularly interesting is that 5G, in addition to allow for higher data rates that clearly are important to support applications such as high-definition video streaming or virtual and augmented reality, is going to be used also by a new, let's say, type of applications, not only serving consumers but also industries. It will be used to serve applications such as manufacturing, automotive, healthcare, energy sectors. So from a timing perspective, this also means that there might be new needs for synchronization. There are, I would say, in summary, a couple of main reasons why synchronization is important in 5G. The first one is the wider use of time division duplex. And the second one, as I mentioned, that there are new applications that themselves need the synchronization that will be supported by 5G. So in the next slide, you can see what is a short summary of what we are going to see in the next couple of hours about 5G and smart cities. So we will start from an overview on the 5G markets, on the status on the deployments, something about the standards, in particular in IGT. I will present a brief overview of what is being done to address the synchronization needs for 5G. We will look at the network impacts due to the introduction of 5G. What are the synchronization challenges? We will see new solutions that can be used to complement the traditional GNSS or PDV-based solutions. And finally, a talk on position, navigation, and time for smart city services. In the next slide, you will see the list of speakers for today. So you can see the biographies of the speaker in the web pages. And I think it's time to to start, and I would introduce the first speaker, who is Chris Pearson, President of 5G Americas. And Chris will be discussing the commercial reality of 5G. So welcome, Chris.
Great, thank you very much for that introduction. This is really an exciting time, and it's a very difficult time, as we know, but it's also an exciting time when we think about technology connecting the world. And without it, where we'd be in the world today with the COVID-19 crisis. So it's an honor to be here, and thank you very much. Next slide. So I'm going to be talking today really about the commercial reality of 5G as an introduction to this great 2 hours of presentations and sessions, because we are in a very critical time for 5G. Next slide. First off, you might wonder, who is 5G Americas? Many of you know us out there that are listening today. 5G Americas is an industry association of leading operators and vendors that are dedicated to moving mobile communications forward, and that includes 5G in North, Central, and Latin America. And we have many areas that we work with, and I welcome you to go to our website to look for more information about 5G Americas. Next slide. So let's talk about where we are today. As far as the commercial reality, today we are at 69 commercial deployments worldwide of 5G technology. And this would be 5G technology that we consider, which would be the 3GPP standard. Now, there are some proprietary 5G deployments that we're not counting in this when we work with our partner Telegeography. But what's really interesting is that we expect by the end of this year to be over 200 5G commercial deployments. So you're seeing a huge uptick and a real commitment by operators to move from LTE Advanced to include in their portfolio of network deployments 5G technology based on the 3GPP standard. Next slide. And that's no different in the United States. The United States is actually one of the leaders when it comes to 5G deployments. We have a very competitive market, and if you look at the three major operators right now, AT&T, T-Mobile, and Verizon, because Sprint actually now is part of T-Mobile, you'll see that they have all been very aggressive in moving forward with their 5G deployments. Now, they might have started in different places. Some have gone, which would be in the lower bands, some have gone in the higher bands, some have gone somewhat in the middle bands, but each of them has been very aggressive in moving forward with really their 5G deployments. And that has made actually, again, the US one of the leaders in 5G because of this commitment to innovation, commitment to deployments, and obviously just the demand of the consumer for 5G products and services. Next slide. And one of the reasons that operators, I think, are interested in making sure they have the latest and greatest technology out in the marketplace is that as we've seen, this data demand is just continues to grow at an astounding rate. We will be looking at and addressing many services and applications and vertical markets when we look at 5G, and especially when you start to think about the smart city applications that we'll be talking about today. But what's critical is also just the understanding that our networks need to continue to improve because of this staggering acceleration of the demand for data. Next slide. If you start to think about how fast we're going to grow, you've seen some global 5G subscription forecasts. One of our really close partners, Omdia, has said that by the end of 2023, which would be year-end 2023, we're going to hit 1.3 billion. And some people might say, "Wow, 1.3 billion, is that a very referenceable? And could this really happen?" So the next slide, please. We looked at other forecasts from other research agencies and research analysts, and what you'll see is, it is actually right around, kind of the median of where most of the analysts are predicting the 5G, technology subscriptions. So as you'll see from this slide, we're about to hit a billion or more in 2023, and actually, as you go to 2025, we're predicting from the various agencies 2.2 to 2.7 billion. So this is, 5G is becoming more and more a commercial reality as we see more and more deployments, and we'll see more and more uptake by subscribers and connections. Next slide, please. And one of the areas that makes 5G so interesting is that we are going to be moving into different areas, and that's so critical to the nature of what 5G is going to do if we reach its promise. And because of that, there's a huge amount of investment and really a circle of investment, because the more that we invest in our networks and the capabilities, the more opportunity we have for new services and applications. So if you look at the numbers, it's staggering what will be invested, as well as what the opportunity is as we look at the other side of things, the creation of jobs, the addition of boosting a country's GDP. It's a really interesting economic and technology investment cycle. Next slide, please. And when I mentioned the opportunity, this slide kind of points out that the global 5G services market size is estimated to be 45.7 billion by the end of this year, and that from 2021 to 2025, it would have an annual growth rate of 32.1%. So when we look at that investment in that economic cycle, we also are looking at the opportunity to go after new services, new applications, new vertical markets, and this would be to reach that potential of 5G and what it can do for our society. Next slide, please. One of the areas that we look to address with 5G is the smart city, and that's what today's sessions will be about. And if you look at 5G and smart cities, it really is about making a city more productive and more efficient. If you think about all the urban problems we have, and it don't have to be urban problems, there's suburban cities that have some of these same issues, you'll realize that you have a lot of opportunity with smart lighting, monitoring, smart parking, traffic sensors, parks and management, all kinds of opportunities to make your city more efficient. Next slide, please. And the same goes for transportation. Why are we building more tunnels and bridges and roads when actually if we're more connected and we have more opportunities from being connected, then your opportunities to run your cities more efficiently are there as far as transportation. Next slide, please. And the same goes for public safety. What if you have the best technology available to your public safety? Again, it's critical need for citizens of the world to have public safety, and LTE and 5G have the opportunity to continue to address that marketplace. Next slide, please. So then you start to say, well, what are the key ingredients? Now, we've shown the potential of 5G and what it can do, what the opportunities are, but what are some of the key ingredients so that really we can reach that promised land of really the portfolio of opportunities that we can address with 5G. So let's talk about them. So network densification and spectrum. Those would be two of the key ingredients that 5G Americas sees the need for at this time. Next slide, please. So first, network densification. Now, when I talk about network densification, I would be talking about cell site deployments and placement. So this is the opportunity to, and really to make sure that we have the opportunity to continue to build cell sites where we need them and how we need them. Next slide, please. And that densification is needed wherever it might be. Now, people think about the urban densification, and that probably gets the headlines more than ever. And if you start to think about the spectrum that is utilized for densification, it makes a big difference in how many cell sites you need. And so that's why if you look at a city, we're going to, if you use what would be called high band spectrum, you're going to be needing more and more cell sites than ever. Even if you go into, say, a suburban area and you want to do a fixed wireless access opportunity, even in those marketplaces, you're going to have to increase your density so you have more small cells into your neighborhood so that you can provide an alternative to maybe your broadband connection, your fixed broadband connection. So wherever you start thinking about 5G, you do want to realize that we do need that densification to meet the promise of the technology. Next slide, please. There's been some studies and some operators and some vendors that talk about, the differences between really a 4G and a 5G density. And depending on the spectrum you utilize, but if you start to utilize the mid-band and the high band, which would be high band beating millimeter wave, you could perhaps need at least 10 times as much density in many areas. Some reports actually have that even at 20 to 30 to 40 to 50 times the density. So again, it depends on the spectrum that you're utilizing, but network density is critical to the potential of 5G. Next slide, please. In the US, we've made some great strides in the last 18 months to try to progress the ability to have more network density. And the key here is really the cell site processes of cities and states and municipalities. We need to continue to work forward to make those cell site processes more transparent, have more reasonable fees, and have a quicker time frame as far as being able to deploy network cell sites throughout the operator's network. Next slide, please. And finally, the other key ingredient is spectrum for the promise of 5G. Next slide, please. So if you start to think about the leadership of the U.S., and the U.S. is one of the leaders as far as 5G, you'll see that we need, as far as a community, a mobile communications community, low, mid, and high band spectrum to meet the promise of 5G. You can't just do it with low band, you can't just do it with mid band, and you can't just do it with high millimeter band. You're going to need the key ingredients of spectrum using all three types of spectrum bands. Next slide, please. And you'll see many parts of the world have focused on the mid band, which would be really considered at this time about the 3.5. In fact, if you think about the rest of the world, they're really coalescing around the mid-band. In fact, in South Korea, they've allocated 280 megahertz of mid-band. In Japan, 800 megahertz. In China, 460 megahertz. So in the U.S., even though we're a leader in the millimeter wave high band, we still have some work to do when it comes to providing more mid-band spectrum for our operators. It is one of the key parts of the story for 5G for the U.S. to be a leader is that mid-band spectrum. The next slide kind of gives you an idea of where we are in the U.S. You'll see that there's been plenty of hard work done by the U.S. government, but again, the area that we're lacking the most is the mid-band. Next slide, please. And recently, the high band spectrum concluded one of their final auction, and you'll see that high band millimeter wave is actually very valuable as well. We have an upcoming auction on CBRS, which has been delayed because of the COVID-19 situation. That's the 3550 to 3700. But our most recent auction goes to show you that spectrum really is the lifeblood of our industry. It's one of the ways that we can reach the promise of 5G. It is one of the ways that our society will stay connected. The mobile communications community needs more internationally harmonized licensed spectrum. So if you start to think about, next slide, overall, where we are today, 5G continues to progress at an astounding rate despite the difficulties of COVID-19 that we're in today. We continue to see that operators are deploying networks. There could be some slowdowns in certain parts of the world, such as Europe and other areas, but in the United States, in the Asia Pacific region, and many others, 5G continues to make that progress. But there are some key ingredients that we need. And we at 5G Americas look at this as a great opportunity for 5G in the next coming years. We think that 5G is has perfect solutions for that smart city to be more productive and more efficient for all citizens. Thank you for this time. It's been an honor and a privilege to be a part of it, and I look forward to questions at the very end of this session. Thank you.
Thank you, Chris. Thank you for the excellent introduction on 5G. And again, if people have questions, please make use of the question window. So we will take your questions during the question and answer session. And it was also perfect timing. So I'll continue. I have the next presentation. It's about a short overview on ITUT, on the group in ITUT that is taking care of synchronization. And if we go to the next slide, this is about study group 15, and in particular the group question 13, that is the expert group for synchronization. Next slide. So study group 15 is the group in ITUT that is responsible for various standards, such as optical transport systems, control plane technologies, fiber or copper-based access networks, optical fibers, and cables. This group is a very large group. Is actually probably the most active group in ITUT, with hundreds of participants and hundreds of documents discussed at every meeting. And in next slide, you can see how this is organized. There are three working parties, main groups, and the one that is more relevant to us, to synchronization, is the working party 3, transport network characteristics. And next slide. So here you see is the group that is dealing with topics such as transport solutions to support 5G in particular. In the recent work, it is working on management aspects of the control and transport planes. And as I mentioned, we also have the synchronization group that is part of this working party. In the next slide, I have collected a summary on what question 13 is doing. So essentially, the scope of the group is to look at the network synchronization time distribution performance, both from the network transport timing needs and also from an end application timing needs. So for instance, we look at what are the needs, in particular in mobile networks, that are those that are in general offer the most, let's say, demanding synchronization requirements. And we look at methods, architectures, clocks, PTP profile, 1580 profile, to deliver synchronization over the networks, looking at redundancy requirements, reliability, and performance aspects. There are quite many recommendations that have been developed by this group. In the next slide is a nice summary we used to update at every meeting, and is one of our most active participants, Helmut Imlau from Deutsche Telekom, who takes care of this very nice table. I think it provides a good summary, but the main point here, you see there are many recommendations that are dealing either with time synchronization, so you see on the right side of the picture, generally under the G.827X series, or a frequency synchronization, the G.826X series. Some of them are still under development, and the work is expected to continue in the next years to complete some important aspects. In particular, in the next slide, I have presented what is probably one of the most interesting points we are currently discussing, and we have a meeting in particular on this point tomorrow. Essentially, we are looking at how the new architectures, specifically also related to 5G, in particular in this case in the front haul, so in the access part of the radio network, how synchronization can be distributed in this very special segment of the network. Looking at what clocks are required, what is the network dimensioning guideline, and so on. Next slide is about other topics that we are considering for the future. In particular, there is work, as I mentioned before, in the study group 15 about the technologies that are suitable for the 5G transport. A new one that is based on an adaptation of Flex Ethernet. It's called the Metro Transport Network. So we need to look into specific needs for synchronization in this case. There are other points we need to address. There is a special setup of a network of reference time clocks. So the master, the time synchronization masters at the top of the synchronization chain, when those are connected together to enhance reliability, the coherent PRTC. We also plan to look at the new synchronization requirements that often emerge from the different standards. And this is about what I wanted to say about, let's say, question 13. Next slide. And if you're more interested in more information about question 13, just send me an email. I would be happy to provide more details. I want to mention also that many of the people in the WSTS steering group are also active participants in question 13. And in fact, we have an ongoing partnership between ITT and WSTS. Okay, with this, I think we can move to the first question and answer session. So we have 5 minutes to direct question to Chris about his presentation or to myself. And I can see one question for Chris about this 5G presentation. So we see higher data rates in 5G, and this may imply issues in terms of capacity requirements for the transport network. So the question is, according to your experience, is this an issue that is found in North America? How operators are addressing this aspect? Are there new investment in the transport network? Chris, you?
Yeah, so you know, I don't have specific information from that I can cite from each individual operator, but yes, I mean when they're looking at their overall network engineering, network planning, and they see that the higher capacity capabilities of 5G, specifically when you start to think about getting more spectrum and the network density with the millimeter wave radios, they definitely are taking into consideration the transport issues. And additionally, if you start to think about the architecture over time, you're going to also see not just the transport layer, but new network elements that provide really a different type of architecture. You start to think about mobile edge computing, so you're getting really some of the computing power closer to the cell sites and so forth. But overall, as far as just straight what would be considered the transport network, definitely operators have to keep that in mind in their engineering, and specifically when you get to those high capacity rates and of the millimeter wave.
Okay, thank you, Chris. I have a question for myself. I was asking who is following the group, question 13, if the network operators are also involved. So that's a good question. I think one important characteristic of question 13 is that it is a mix of participants with different, let's say, perspectives. So we have both network operators, I would say from all over the world, from China, Europe, North America, and of course several system vendors, clock vendors, of course, and this allows for very good discussions and looking for, let's say, the best solution that is suitable for everyone. Let's say, I think it's a group about 30 to 40 people following the group generally. Okay, let me see. Okay, I see no other question. I think you still have time. At the end, as I mentioned, we have a second time slot for questions, so you can still send a question to myself or Chris, in addition to the other speakers. Okay, I think maybe we can move forward, as I see no other question for now. And the next speaker I would like to introduce is Barry Dropping, Associate Director of Product Line Management in Microchip. And Barry will give you some insight into Microchip services and products. As I mentioned, Microchip is sponsoring this session. So Barry, welcome, please.
Thank you, Stefano. First, we'll say Microchip is very proud to be associated with WSTS for many years, and in particular, we're quite proud to sponsor this webinar event today. With that, I'll move forward and on the next slide and give a brief overview of Microchip, just so you know who we are. We're really a leading total system solution provider. We really focus on a lot of different areas. One of our deep areas of expertise is clock and timing solutions. We'll talk a lot about that in a moment. The company size is on the order of $6 billion annual revenue run rate, and we employ approximately 19,000 people worldwide. Our headquarters in the U.S. and the state of Arizona. Next slide, please. I'll profile really the breadth here of our timing and clock product lines. We are broadly represented across the entire ecosystem with everything from the smallest, most basic oscillators all the way up to the lower right of this panel where we look at the atomic clocks that go into the time scales, the ultimate source of timing that drive the GNSS systems, that drive the national time scale. So we really play across that full range. On the next slide, I'll look at how that maps into 5G that we're talking about today. We're really deeply entrenched in the 5G infrastructure. If we look at all of the elements of infrastructure use our components, and a key element in there is our timing systems. These are the source clocks that initiate the timing flows for 5G. 5G is highly dependent on synchronization and timing, and has really challenged the industry to generate very robust, protected, and resilient clock infrastructure. If I look at the enabled markets, we also play quite heavily in all of the enabled markets. Today we're talking about a key one with smart cities and smart automobiles, et cetera, et cetera. So it's really a game-changing technology for the next decade forward, as Chris talked about. On the next slide, I'll talk about the timing systems. These are probably the products we're most known for by the community here. These are the reference clocks, the timing servers that go into the 5G networks that really, again, become the source clock for the timing flows. And at the bottom of this, I showed our pedigree. I've really been associated myself with WSTS for 20 years now, dating back to Symmetricom that was acquired by Microsemi and now recently acquired by Microchip. So many of you may know us by different names, but I'll assure you it's the same team. When you come physically to WSTS in the future, you'll see us there, and we'll be happy to meet you as our Microchip team now. On the next slide, I want to talk a little bit about how these fit into the critical infrastructures. In the beginning, WSTS was very much focused on the communications, but this charter of WSTS has broadened now, and the critical infrastructures dependent on timing are far-ranging. The financial industry, the power grids, of course, all the wireless communications, high dependence. But on the next slide, I want to emphasize a point for the rest of the day that conversation is changing. While the precision is important, the accuracy is important, what's really carrying the conversation now is the security of the national infrastructure. And that security is paramount as we move forward. On the next slide, I'll finish just with a little overview of the timing hygiene. The conversations we're involved with in planning today look to the hygiene and really trying to understand, is the sync secure? Is it authenticated? Do you have the visibility of the synchronization? Do you have the analytics to really analyze the source and the purity of the synchronization? And then very importantly, the resiliency. What is the backup? If you're dependent on GNSS, if GNSS is spoofed or jammed, what's your alternative? What's your backup solution? This is the deep engineering discussions that are going on today, driving the networks forward. Okay, well, that's a little bit overview of Microchip as the sponsor for the event today. Thank you very much, and look forward to the rest of the session. Stefano, back to you.
Yeah, thank you, Barry. That was very interesting. So I would now like to introduce the next speaker, Anand Ram, who is the Vice President of the Business Development at Calnex Solutions, and he will discuss 3 steps to 5G. So welcome, Anand.
Thank you, Stefano. Hello, everyone. My name is Anand Ram. I'm the VP of Business Development for Calnex Solutions. Calnex is a vendor of test equipment, specifically focusing on the area of timing and synchronization. So I'm delighted to be able to speak to you today, and my presentation is titled 3 Steps to 5G. It seems like a small number of steps to deploy an incredibly complex technology, but what I've tried to do in this presentation is really to try and summarize 3 considerations which are relevant to this form of timing and synchronization as a vendor or an operator or a supplier to prepare for the deployment of 5G networks. Next slide, please. So the topic, the title of the presentations could also be 3 considerations to take into account when migrating to 5G. So the 3 topics we're going to be talking about today are really the X haul or the NE haul, the change and the evolution of the transport network that connects to the radio base station. We've cheekily entitled that What the Haul. The second topic is really specific to timing and synchronization, some of the considerations, changes and challenges within the field of timing and synchronization relevant to the deployments that we've been seeing when working with vendors and operators for 5G technologies. And then the final topic is really looking at the area of disaggregated platforms. We've called it disaggregation and virtualization. Different people call it different things depending on what they mean, but really here we're going to talk about the topic, again, of these new generation of platforms that are relevant to deployments of 5G networks. Next slide. So let's look first at the transport portion. So the evolution of transport is specifically about the evolution of what we call the front haul. Now, the original front haul concept to the left of this slide was conceived as primarily a fiber connection to split the functionality of what used to be the base station into a baseband unit connected via a front haul, usually CPRI connection, to the radio unit. This allowed the baseband unit to be located, and the control and functionality of that baseband unit to be located remotely from the front-end antenna of the radio interface of that base station. So the front haul was conceived as a split of the functions of the baseband and the remote radio unit, and establishing a dedicated, usually fiber connection between those 2 elements. Then the front haul concept evolved into what we call the centralized radio access network. The centralized RAN was really the concept of trying to centralize a location of these baseband units. So the concept of a baseband hotel, which is a great name, but really it was a co-located facility where multiple baseband units that controlled multiple radio units were located in the same place. Obviously, this allowed more units to be co-located, potentially saving costs in that regard. But also it meant that these connections between the baseband hotels and the radio units were often a little bit longer than they were in the first diagram. So the main difference with the centralized RAN was really the co-location of the baseband units and the fact that these the distances of the front haul connections between the BBUs and RRUs had to increase to cater for that. But it was the first step of the evolution of the front haul. What we really want to look at here is also the further evolution of that front haul architecture. And of course, this is just summarizing it. There's a lot more extent to which this front haul can be split. But I've just simplified it to split what we call the centralized unit, the CU, and then the distributed unit, the DU, and the RRU. So again, what used to be the baseband unit, BBU, is now split into the CU and a DU, and we introduce the concept of what we call the middle haul between the CU and the DU. Now, why would you do this? Well, again, it's fundamentally to further split and make the network more efficient, so that if you want to start splitting the functionality of each of these components, you can actually do a lot of the processing and handling of mobile communication at different parts of the networks. So this flexibility means that, of course, the network and deployment model is more flexible. Also, it means traffic and traffic loading can be handled much more flexibly. So there's benefit in migrating to the right side of this network, particularly with the growing data demands of 5G. But of course, the other thing that you can do now is then you can start networking this connection. What used to be a dedicated fiber connection can now be conceived as a network connection. And so that's what this slide is showing here. When we move from what is a dedicated fiber connection to what is, and usually an Ethernet network connection, the big change that you will see is that you go from what is effectively fixed and known characteristics of fiber, things like latency and asymmetry, with very, very limited things like packet loss and jitter on that dedicated fiber link. When you move to a networked front haul or any haul connection, you now got all the characteristics of the network coming into play. So what used to be a relatively fixed, low and known latency and asymmetry and almost no packet loss and jitter is now becoming variable amounts of latency, loss and jitter. And of course, this is one of the key considerations initially for the vendors, but of course later for the operators as they deploy this as well. The management and the protocol between the baseband unit and the RRU was originally designed for a dedicated and known fiber link. Now it's going through a network, and these changes need to be validated and tested to make sure everything still works, moving from a dedicated fiber to a network connection. Next slide, please. So the second consideration we were talking about is really timing and synchronization. And really we're looking at three subtopics here. First of all, again, we work with a number of operators globally in terms of their deployment projects for 5G, as well as the vendors supplying to these operators. And what we're really seeing, the big game changer in the evolution of timing and synchronization in the network for 5G is really happening with the migration to standalone 5G. As well as technologies like dynamic spectrum sharing, DSS, which allow 5G to effectively utilize some of the spectrum that was being used for 4G beforehand. So what we're seeing in operators around the world is that the first rollout of non-standalone 5G, there was some change in the timing and synchronization architecture, but the real change is now happening as those networks migrate to standalone and incorporate technologies like DSS. And of course, the question a lot of the operators are asking is, well, what's the right deployment model? What's the architecture to use? Which profile? How much accuracy do I need? So these are questions that each operator is asking, and we're not expecting to answer all those questions in the next 5 minutes. However, we'll give you some examples of what one operator is doing. And then, of course, in timing and synchronization, does 5G introduce any new challenges or issues that we haven't had to deal with before? Next slide. So in terms of the architecture, this is simply an example of one deployment where this is a major tier 1 operator, and their deployment model for PTP timing in the network involves installing what we call an edge grandmaster, which is a GNSS receiving device, which then forms a grandmaster connection for PTP or precision timing protocol, which is located or co-located with the central unit, the CU. You then have effectively a maximum of 2 nodes, with this, namely the CU and the DU, between the grandmaster and a PTP slave. They use the 8275.1 profile. The G8275.1 is the full timing support profile, which means the CU and DU in this architecture are PTP-aware devices. And by deploying with this model, there's plenty of headroom to meet the network 1.1 microsecond limit that's required for the whether it's 3, 4, 5G RF technologies to work. But of course, one of the challenges with this deployment model is you need to deploy an edge grandmaster per CU, and that could be a pretty significant investment. But this operator has chosen to do that. And it obviously has benefits in terms of providing a lot of headroom to meet the network requirement for timing and sync. There are, of course, other options. You can put fewer grandmasters deeper in the network. You can use partial timing support. 8275.2 is the partial timing support profile, which again means that not all the elements in this link have to be PTP aware. And of course, there are models around the world, there are also operators around the world who are using the concept of what we call coordinated primary reference time blocks. These are the core grandmasters located in the core of the network. They are then coordinated, which leads to a greater degree of coordination and accuracy. And then that accuracy is fanned out to a wider network, and still achieving that end accuracy requirement of ±1 microsecond. So the answer to the question is, what is the right architecture and profile? Is unfortunately there isn't one right architecture or profiles. But the good news is there are many options, and the ITU-T recommendations that Stefano talked about earlier in this presentation give a framework to give the operators around the world lots of different options for deployment. But as I say, there are lots of options, and we're seeing that the standalone evolution to standalone or to DSS is what's driving the investment to deploy PTP in the network. Next slide, please. So looking ahead in terms of moving from the architecture to the question of, are there any specific new challenges or issues with deploying synchronization or synchronization 5G? Two of the things that we've picked up in discussions with vendors and operators, the first is really the desire to remove guard bands. Now, it was common in previous generations of mobile network deployments where you had these guard bands between frequencies used by one operator and another operator, really to try and minimize the interference between the frequencies used by one operator and another. 5G is, of course, bandwidth hungry, therefore spectrum hungry, and so there is a lot of drive and desire to remove these guard bands and more fully utilize the spectrum for transporting data over the air. So once you remove the guard bands, you potentially have obviously more greater potential of interference in those edge areas between one operator and another. So this is something new that we're seeing. We're seeing the need to check synchronization in the network. We are also seeing regulators in certain countries getting involved, because now it's not just operators A's job to make sure that their synchronization is good. It's also operators B jobs and operator C's job to make sure that synchronization is good. So I think that here, one of the key things we're seeing with 5G is that with the removal of these guard bands, or the idea to remove guard bands, the need to synchronize to the same reference is important, and often the regulator has to get involved to mandate for that. And then secondly, the need to check the synchronization, not just for one operator, but all operators, is becoming more and more critical, particularly around frequencies that overlap between them, or at least adjacent frequencies between the operators. So that's one thing that we're seeing in terms of a challenge. The other challenge we're seeing with the front haul architecture and the split of the CUs and the DUs, as well as the RRUs, is really now that in the past, we used to have radio equipment that had filtering capabilities, which allowed short-term wander to be filtered, or clock wander to be filtered out, and allowed it to work correctly. Now, at the moment, we have the functional split of the front haul, and the remote radio units are very often designed without this filtering capability. They tend to be in environments which have greater environmental stress in terms of temperature, vibration, and so on. And all of this stuff impacts the ability to filter out short-term clock wander. And potentially the 50 parts per billion stability requirement for the RF to work is potentially being breached when this short-term filtering doesn't happen. So one of the things to watch out for is that, to summarize it and very simplistically, the migration to a front haul architecture with RRU could mean that the 50 parts per billion requirements for frequency stability is now broken because the low pass filtering isn't there. So again, this is a discussion that's happening at the standards bodies in terms of what do we do about it. Next slide. And then finally, I wanted to focus on the topic of virtualization and disaggregation. So disaggregation is really the concept of what used to be integrated software and hardware, disaggregated into a platform where software is running on generic, what we call white box hardware. Now, this is a movement that we're seeing happening a lot, particularly with the migration to 5G. This concept of virtualization or disaggregation has been around for quite a while. However, we're seeing it being implemented for 5G networks, primarily because there's a lot of interest in migrating the infrastructure of 5G into the data center using these white boxes. The integrated platforms to the left Of course, you had an extensive feature set. You had lots of different hardware form factors from the different vendors. It came from the vendors all integrated and tested, and you got support from a single vendor point. That was the benefit of the software and hardware architecture. That's what the integrated software and hardware architecture. As you move to a disaggregated platform, one of the key benefits here is that you might get faster software feature development. Vendors working just on the software portion could bring out new software features faster. There's independence of the hardware platform, so you could buy white boxes from any vendor, and it gives the operator new deployment and operational options, and eventually, maybe not on day one, but eventually some cost benefits as well. So there's benefits in migrating to this new architecture, but there's also challenges. Next slide. And primarily the questions that operators are asking around the disaggregated platforms is, well, if it doesn't come integrated, then who will integrate? Who's going to test that this all works? And who do I call for support? So these are good questions. They have different answers for different operators. However, bear in mind that the topic of disaggregation is an active projects in multiple groups. So I've named a couple here. I've named the OCP, ORAN, and Telecoms Infra project. They're all running projects where they develop specifications and methodologies for development and deployment of disaggregated platforms, but also they run plug fests where this equipment is tested, proof of concepts are done. So really all of the vendor community and operator community around the world are active members of all these groups. They all have a collective and active role. So the answer to the question, who will integrate or who will test, who will support, is really, it's work in progress at the moment, but there is a lot of work going on to try and make disaggregated platform more acceptable. But of course, there are still challenges in terms of a non-integrated platform, and that's a driver for testing, which is what Calnex does. Okay, next slide, please. And just to summarize the presentation, the three considerations for an operator or a vendor involving 5G in terms of the timing and synchronization issues. First, that the network parameters are changing, and so we're moving from a dedicated fiber to a network in the front haul, and that could impact communication, protocol control, and of course synchronization. 5G standalone, we believe, is driving new architectures and deployments of an investment in timing and synchronization for 5G. And of course, be aware that there are some new gotchas for 5G timing, namely the potential removal of guard bands and the idea that short-term clock wonder could manifest itself in the remote radio units. And then finally, the 5G infrastructure, we believe, will be a lot of disaggregation in data centers. Ultimately, this provides new challenges, and we believe that there's a collective effort in play to integrate, actually, I should say, specify, integrate, test, prove, and deploy disaggregated platforms. Okay, thank you very much. That's the end of my presentation. And now over to the next presenter.
Okay, thank you, Anand, for a great presentation. And I would like now to introduce the next speaker, Morten Wåström, system developer at Ericsson. And Morten will discuss sync accuracy challenges in 5G. Please, Morten.
Thank you, Stefano. It's often claimed that 5G will require better accuracy than 4G, but this is generally not true. But there are some use cases that might require attention from vendors and operators, and I will discuss 3 of them in this speech. Next slide. The baseline here, I think, is that ITT has developed a method to dimension the network where it has allocated 400 nanoseconds to the RBS itself. So this applies for TDD then according to 3GPP. But 3GPP is also studying 3 use cases: industrial IoT, which require high accuracy time transfer across the 5G network. Integrated access and backhaul is to use the actual radio interface for transport, as not only for the UE access. And UE positioning there are some unrealistic expectations, according to me, in this own synchronization accuracy to provide positioning accuracy. Next slide. First, we need to know what are we synchronizing. The synchronization accuracy point is at the radio antenna, and in the radio interface there is a frame. It's a sort of TDM frame, and it has a duration of 10 milliseconds, and its number of frames are numbered up to 1024 frames, and then the numbering restarts. And the error that 3GPP allows, the maximum error, is the deviation between the frame starts of these SFN frames. So both the number and the frame start, they have to be synchronized. And for TDD, this frame numbering is used to create a guard period where both the base station and the U has to be silent. And part of this guard period is used as an allocation for timing accuracy. There are also applications in the UE that require simultaneous reception. So the both base stations, they have to be synchronous because the UE need to receive them simultaneously. But in 3GPP, these use cases, they require co-located antennas. Next slide. So we heard about what an RBS could be, and we heard about the split between CU and DU. But it's more than that. Even the DU could be complex, or the RBS with the radio units. It can contain several radio units. It can contain multiple DUs and multiplexers. And there are shared radio units, so you can provide both LT and NR on the same air interface. And all of this has to be synchronized. And all of this, if you're running TDD, has to meet the 1.5 plus minus 1.5 microseconds. Also, if you lose synchronization, then the DU has to provide time holdover. If you look at the 2D RUs here, which are co-located, you have a coordination feature here that requires better than 130 nanoseconds accuracy. But it's only between those two radio units or between those two antenna points. So you can understand that it's easier to provide that type of accuracy there. It's not required from the network itself. Next slide. So if you want to improve the accuracy of the RBS itself, I mean, you need to go to a higher degree of integration. You cannot have this complex RBS. And the best you can do, of course, is to integrate everything into one box. So you have the DU function, the radio unit function, and also the antenna integrated. And this is what will happen actually in the high band domain, because you need the integrated antenna to facilitate the beamforming. But vendors and operators will also need larger macro base stations that will have difficulties in meeting these stringent requirements. So what are the bottlenecks for accuracy? I think I mean, you're familiar with PTP or GNSS accuracy problems. There's also a holdover margin for the GNSS outage. I mean, if you lose the GNSS signal, you still have transport. But if you lose transport, you also lose PTP most likely. But in the radio domain, you also have inaccuracy contributors, like radio signal filters, for example. They could be of the cavity type and mechanical structure. They can be compensated for temperature variations, but not completely. So it's creating dependency to group delay. So applications require much higher accuracy. They require special RBS designs and special sync distribution designs. Next slide. The first challenge is industrial IoT for time-sensitive networks. So here we see a picture with a time-sensitive network that is located on two sides of the 5G network, and the time of the time-sensitive network has to be transferred across the 5G network. And the method applied by 3GPP here is a sort of distributed transparent clock, if you're familiar with that from PTP. So it requires a time-stamping function at the edges of the 5G network. And if they are accurately synchronized to each other, these time-stamping functions, you can calculate the residence time of the TSN timing packet that goes across the network, and you can compensate for it. And the challenge here is that in the TSN community, there is a requirement that any point in the TSN network has to be within 1 microsecond. And that leaves less than 1 microsecond for the 5G network, of course. But this has not been concluded in 3GPP yet, how much budget the 5G network will get. And if we look at many of the components here that contributes to inaccuracy, I think the air interface is a critical point. And in worst case, the transferring PTP packet will pass the air interface twice. And if you consider today that the accuracy requirement is 1.5 microsecond, you can realize that here you need a special RBS actually to provide better accuracy for this use case. Next slide. Integrated access and backhaul. The goal of integrated access and backhaul is to provide transport connectivity to radio base stations without having fiber or a fixed line connection to the nodes. Instead, you're using the radio interface itself and create a transport link to the nodes. You can synchronize all these nodes with GNSS, and then the characteristics of the nodes, they will be the same as an ordinary node, and it's obvious that this 3 microsecond requirement between those two chains, the end nodes there, will be met. But these IAB nodes, they might be placed in urban canyons, and the capability of GNSS to synchronize nodes might not be perfect. So we will be looking at over-the-air synchronization of the IAB nodes. And then you end up in the same type of accuracy problems as with PTP. Every hop will decrease the accuracy. And next slide, we'll see what we can do about it. You remember this guard period. It consists of 3 properties. It's the delay in the air of the signal, it's the switching on and off of amplifiers, and it's a small allocation for synchronization accuracy. You can actually gain more headroom for sync by increasing the guard period. That would take some of the capacity of the air interface, around 4 or 5%. Or you can sort of distribute the available synchronization accuracy budget between these multiple hops, and then you get the dependency in how many hops do you allow. And you might have to sacrifice some of the holdover of the donor node, and that will impact availability of the network. Next slide, we'll look into the next. It's a UE positioning use case, and this is a tricky question because it's easy to imagine an application that can require any position accuracy, really. So it's hard to make a generic spec of it. Some methods rely on accurate synchronization, but far from all. I mean, there are round trip measurements or heuristic methods you can use to gain the position of the UE. There's one example down here from FCC for emergency call with not so stringent requirements. And traditionally, the methods has been by GNSS have been complemented by OTDOA, which actually use accurate sync. And if you're going to use a network-based method, you can see next slide how you can improve the accuracy of positioning. The positioning is calculated by an offline positioning server, which collects data from the base stations and the UEs. And if you're able to measure the actual sync difference between base stations over the air, the delta SFN as I call it here, you can use this delta SFN as a compensation value in the calculations of the positioning server. So you don't actually have to provide better synchronization of the nodes. And using the raw measurement data will actually provide better accuracy than trying first to synchronize the nodes to each other. So next slide, we will see a summary. So first, a modular and complex RBS, it can meet the 3GPP requirements of 1.5 microseconds. But for this type of RBS, the 400 nanoseconds will be required, since it will be used by hardware components and time holdover. Fully integrated RBS could provide better accuracy for IB, IoT, and positioning. But I mean, these will be special RBSs, and the cost will be higher, maybe. And will vendors and operators pay for that? I think instead you should look at restricted deployments for industrial IoT. I mean, it will not be required. This high accuracy will not be required everywhere. For integrated and access and backhaul, you can increase the guard period and thus reduce the requirement for better accuracy. And for positioning, you can use non-sync dependent positioning method, or you can use this SFN delta measurement to improve the accuracy of the positioning. And by looking at the network, where do you need these special accuracy requirements, you can reduce the cost of deployment for sync accuracy. Thank you.
Thank you, Morten. That was a good insight on what base station vendors have to do to make everything working. So I think we are a few minutes in advance. Maybe what I would do, because we during let's say the moving from one speaker to the next one, there were several questions received, and many of them were let's say directed to my presentation. So maybe before moving to Umut, I can take maybe a couple of the questions just to make a good use of time. And so there were a couple of questions about standards, so probably directly to my presentation. There was one question whether, in addition, I guess, to ITT, there were other groups dealing with synchronization, like in IEEE and IETF. And indeed, in IEEE, I can answer there is a lot of work in the, for instance, in the precision time protocol standard, the IEEE 1588, that has recently been revised with version 2.1, and new work is starting to add further enhancement to the standard. So IEEE 1588. In IEEE, as related to synchronization, there is also work in other groups, like there has been a work on profile for front all over Ethernet with a lot of synchronization aspects, IEEE 802.1 CM. There is a work ongoing now on synchronization in industrial automation. It is a joint work with IEC and IEEE. And of course, offline, I can provide you with more information. I can take one more question and then we move with the next speaker. What applications are driving tight synchronization requirements? That's a good question. So I think Morten in the previous presentation, let's say, provided a good summary of what are the actual synchronization requirements in 5G. I would say when we speak of tight synchronization requirements, I understand tighter than maybe 1 microsecond. Sometimes we have seen numbers like 100 nanosecond or something like that. I would say very often those type of requirements are very special. Sometimes there are positioning methods, as mentioned by Morten, that require such accuracy if you want to achieve a very accurate, let's say, positioning using the OTDOA methods, but there are other methods that can be used. Then there are applications that can be served by the radio network that themselves require synchronization, as mentioned by Morten. So I would say that this question has actually been covered very well by the previous presentation. I take the last one that is very short. When can we expect to see work on telecom profile interworking? So that's a good question. So as I mentioned before, in question 13, work has been done on defining telecom profiles. There are several recommendations like G.8275.1, G.8275.2. And indeed, the work has already started to define, let's say, rules, guidelines, how to make those profile interwork. A good reference is G.8275 as an example. So I think work is already starting. There are a few points to be still addressed, but I think it's on a good way. Okay, maybe we can now go back to the agenda, and I see Umut waiting for that. So I would, let's say, introduce the next speaker, that is Umut Keten. He's working as a lead architect at Turk Telecom, and he will present an alternative approach for time sync over the telco network. So welcome, Umut.
Thank you so much, Stefano, and thank you, the chair, everybody, for having me for this meeting. Well, actually, this is much harder than actually standing in front of an audience, but let's give it a go. So thank you, everybody. I will try to explain an alternative way to transport time synchronization over telco networks. I'm really glad about the agenda because my presentation will fit exactly in where the Ericsson presentation of Martin and the Calnix presentation of Anand left, and I will try to explain a little bit what we did. So if we can go to the next slide, I will present an agenda. I will talk a little bit about the Turk Telecom Group because we are not that much known to everybody and what we're actually doing. And after that, I will try to, I called it says there the problems, but I will talk about the challenges about providing time synchronization or distributing them. And I will talk about the solution, what we have come with, and how this works. And we call it the Turkish-Swedish approach. So if you can go to the next slide. It was a little slide about me, but we already saw that. I have 18 years of telco and broadcaster networks experience. And actually, with my good colleagues in Sweden, we came up with a new way of transporting time. So if we can go to the next slide. The Turk Telecom Group exists of it's an umbrella company. It's all about Turk Telecom, which is the main operator inside Turkey, and we have sub-companies below it, which are Turk Telecom International, Innova, Argela, Cebit, and Estes. If we can go to the next slide. This is a little bit about in numbers. So we have around almost 48 million subscribers, almost 33,000 employees, and we are the biggest employer in Turkey. 304,000 kilometers of fiber going to 81 cities. If we can go to the next slide. And now we're going to really discuss what's going on and our view. So in our point of view, there are actually two things going on. There are challenges and threats to using only GNSS. And deploying or distributing PTP, hold on, there's a problem with my screen and everything is frozen. Just a second. Okay, I'm sorry, but my computer froze and I couldn't see anything. So I'm picking up where I was. My apologies to everybody. So in our view, a major part of the 5G evolution will be about meeting the requirements of phase and frequency demands. So networks based on time division, duplexing, and CRAM, these are the techniques that will require phase and frequency and timing synchronization. So in our position, and like us, a lot of operators are trying to design networks capable of delivering these demands. So to prepare 5G base stations requires an accuracy on these clocking. And in this scenario, or in the current scenario, this is up to a maximum of 1.5 microseconds. So here we have is what we're going to use is actually GPS GNSS as a primary clock source, and as an addition, PTP delivered from the network to be a supplementary or sometimes even a main. But here comes the biggest challenge of all. Because of limitations on existing networks and network elements, what operators currently have in their networks, you might have to locate a lot of ground master clock technology close to small cells and end application. So in terms, this will be also a big cost, not only implementing, but there will be also a part of maintaining, operating, and even monitoring, and also at the end locations, still going to sites and visiting and monitoring on those base stations if they still get the proper time. So these are all things that are not really fully discussed yet. It's all about how people are going to invest and where they're going to place. But after that, there is also the part, the challenge of how are you going to operate it. After this implementation and operating, you're also going to have issues of troubleshooting everything. This is also a big thing, because if in the end somebody will not receive a GPS or GNSS signal, or it's or the signal is out of the maximum 1.5 microsecond range, then you have a problem, but this problem needs to be solved, and who's going to solve it? So let's discuss about the main problem which you will face with GPS and GNSS. In our point of view, we consider that overall GNSS will provide a high degree of reliability. But this is not applicable for most mobile base stations in at the end domain. The main issue from our point of view is that each individual base station and its GNSS receiver becomes a challenge on its own. So if you have a location and you have a lot of base stations, and 4 of those base stations will not have a problem, but maybe 1 of them, you will need to locate that one, fix that one, operate that one. So every base station becomes a challenge on its own. And even the shortest outage of signal, so GNSS signal outage, may affect your services. And depending on the service characteristics, this can become a real huge problem. You can fix this by having oscillators at every base station or at every critical location. But even there, the bigger challenge will be for the times when the GNSS outage will be beyond the oscillator's limitations. So a loss of synchronization is a big thing here, because 5G is not like the previous technologies. The moment when you lose or fail synchronization, you will lose your services. And in our point of view, like this is such a critical thing now that we need to solve. If you can go to the next slide, please. Now currently there are standards provided, like Stefano advised earlier on. We have the 8275.1 and 8275.2 is how to actually deploy your equipment so you can actually bring PTP to the end location. These are really, really good described standards. They, in a nutshell, they provide actually a framework what you can work with. But in the end, every architecture for every operator will be really, really different. And in most scenarios, it will be very, very hard to accomplish because of the current networks and network elements what you have. So if we can go to the next slide, I will try to explain what is going to happen when you try to implement a full on-path solution. So when we are transporting PTP from point A to B, because this is how we're going to transfer time, the packet will actually can traverse in a certain way to point B, and the way back can actually be a little bit different. And to understand how time mechanics works here and how it is described, if the moment that I know that I need to distribute time, and let's say Stefano, which is a good friend of mine as well, if he requires to know the time and I know the time and I will have to send the time to Stefano, I'm going to try to use an analogy. At point A, when I look at my clock and I see that it's 12 o'clock and I will need to relay this to Stefano, then the only means that I can do is write the time on a note, give it to the postman, and send them on path and let him arrive at Stefano. And the moment that Stefano receives this piece of paper and he looks at the time and he sees 12 o'clock, the time traversed in between is actually, it's not 12 o'clock anymore. So to solve this, actually the standard describes, or how the PTP actually works, is that it expects actually the postman to come back to him again. And in a nutshell, it actually calculates then the time that has passed for the postman to go to Stefano and to come back and to make an educated calculation on what has traversed. The problem here is not the standard, because this is the only way how you can transport time. This is the necessity. The problem is the road that the postman needs to take, and in this case, for every telco network, it is an MPLS network. And don't get me wrong, I don't say that MPLS networks are bad. They're perfect for data, they're perfect for services, they're perfect for to apply quality of services, but it's a terrible medium to transport time, because it's unreliable in terms for time. Because what will happen in a MPLS networks is, if we can go to the next slide, please. Can we go to the next slide, please? Okay. I only gave an example here of 2 layers. Sometimes it's even 3 layers. It's depending. It's not only the MPLS networks, which is actually transporting the time. To go from point A to B, a packet will traverse also through a fiber optic network. So in this, I've written it down as DWDM, but some people use also ONT networks, so optical OTN networks, the optical transport networks. But going from point A to B, it actually needs to traverse over a few or multiple layers. And both layers and the operations of those two layers are both separate from each other. They are not aware from each other. So when you actually transport from point A to B, it goes to, maybe it stays on the first hop, it stays on the MPLS networks, but the second hop, it needs to traverse over the OTN network. And then it goes back to the MPLS networks. So every part of this network piece, they all need to be PTP aware to have a good transport. You can traffic engineer this, yes, but the moment you have traffic engineered this and it takes a path, the underlying path could have a fiber cut, which happens, or there's a card upgrade, there's any kind of thing. So if there's a switch over and the OTN networks goes over to a protection network, and this part of the network is upgraded or not upgraded, or there's any kind of issue, again, your timing will be off the charts. And this is what we have seen in our network, and this was becoming a problem. And the problem was always reactive for us, because the endpoint, when it receives a time and it's out of the charts, it's being reported as a ticket to the operations team, but the operations team doesn't know how to troubleshoot it or where to troubleshoot it, because they only see the MPLS part of the network, or the other operations team, they only see the OTN part of the network. But where did the outage happen? Where was the reroute? And in the time before the time you got it fixed, the outage is already too far away. So we had to figure out a way to actually fix the problems that our networks are presenting for time transfer. So we came with a different solution. If you can go to the next slide, please. We did a different approach. Next slide, please. We called it the terrestrial approach because we are working together with our Swedish counterparts, and we have decided to use DTM. We are creating actually an overlay network over the MPLS to fix the problems. So in short, what is DTM? DTM is a time division multiplex and a circuit switched network technology that combines switching and transport with dynamic reallocation of that. So what does this tell us? So it can provide every type of service like IP does, but it does this with varied bit rates with channels. And the most or the best thing of DTM for providing actually time transfer here is a TDM technology. It's a time division multiplexing technology. So it's an ideal candidate to transport time. So what we do now is, if we can go to the next slide. We create another layer on top of the other layers. And this layer is actually fixing the indiscrepancies of the layers below. There are multiple technologies and algorithms inside DTM that actually clear out the indiscrepancies of MPLS and the underlying layers. So what it actually does, it creates on a virtual circuit point to point, and this virtual circuit actually fixes the jitter and latency issue with the minimum time sampling algorithm, or how we call it. And to transport the time and to select the best time packets, we use a minimum block sampling algorithm. So like the example what I gave before with sending a note to Stefano with the time, what we do here now is when we send the note, or when we send the time and we give it to the postman now has its own road with no asymmetry. So it's a flatted out road, and the time that he needs to go to Stefano and come back is really, really stable. So the calculation of the end time, what it should be, is much, much easier and much, much precise. And in our opinion, with the current standards and the PTP protocol, this fits in best to transport time to distant locations. Can we go to the next slide, please? At the time, we have tested this in our network, and our results are really out of this world, because we can transport time with over 1,000 kilometers distance, with 14 hops going to the end location and 11 hops back. So there is asymmetry as well in the network. In the beginning, we were below 138 nanoseconds offset, and we have actually made this better. We are now under the 50 nanoseconds offset. The bad thing now, the only bad thing now is because of the COVID, we actually wanted to deploy and put this out to live 5G sites, but because everything is actually postponed, also this is postponed, but I actually, with this meeting, I wanted to display the results of the live networks, of the live 5G sites, but that is hopefully for the next meeting. But so what we have here, or what we're doing here with Turk Telecom and with our Swedish counterparts, is I think we have the holy grail of transporting or doing time transfer from point A to B, still using the underlying networks, but we don't need to upgrade them anymore. So we don't need to.
Sorry.
Yes.
Sorry, I have to ask you to wrap it up because we are, let's say, out of time. Thank you.
I will wrap it up. We're at last slide, but yeah, that's it. I think we have a future solution here in our hands, and hopefully I will present more results in the coming time. Thank you, Stefano. That's it.
Thank you, Umut. That was very interesting. So I'm sorry that I had to stop. I think you went through all the messages. I think they're very interesting. Okay. So I would like now to introduce our last speaker for today, John Hill, who is technical specialist at Microchip, and Joe will discuss smart city precision timing. So welcome, Joe. Joe, please check you are on mute. We cannot hear you.
Yeah, sorry, beg your pardon.
Oh,
yes,
thank you.
Thank you very much, everybody, and thank you to Atis for hosting us today. Very daunting following all these wonderful presentations, I have to say. So today I'm going to focus on essentially how you cluster an ensemble of micro clocks to develop a micro positioning, what we call position, navigation and time implementation. It is today focused on autonomous vehicles, but we do think it has other applications going forward. The next slide, please. I'm going to go very fast today and just pick out the main points in the presentation so that I can give a little bit of time to the main drive of this presentation. But it's obvious that navigation safety has been well understood to have links to precise time since the mid-1800s, when they had a huge series of collisions on rail tracks. The Royal Commission in 1849 came out with an extremely pithy statement. Both trains, it said, should not have been in the same place at the same time, a rather British understatement, I think. And we would say the cause was poor clock synchronization. In other words, there was too much error between the cities, Bristol and London, 10-minute time error. They were not synchronized, and therefore there was a plus or minus 10-kilometer uncertainty for location for trains. Next slide, please. Now, what are the positional requirements and situational awareness parameters for autonomous vehicles that we are driving forwards today? And without going into too much detail here, there's a huge volume of research on this subject. It's generally accepted that today we have a plus or minus 5 meters fuzzy location in tens of seconds. And that can be more or less mitigated by proximity centers and so on. But the actual absolute continual location requirement in time for an autonomous vehicle, that's a vehicle where there is no driver basically, is plus or minus 2 centimeters, both in lateral and longitudinal accuracy. And some figures below on this slide, as you will see, in terms of meters per second that vehicles travel. Everybody understands that. And then if you want to look at the National Health Safety Institute of autonomy levels, you can investigate that. These figures are taken from there. Next slide, please. Now, autonomous driving in smart cities. So how can we achieve a 2 to 5 centimeter accuracy in real time at normal driving speed? The conclusion most of the autonomous vehicle development entities has come to is, well, we need a huge AI in the vehicle. We need in-vehicle intelligence and control, millions of AI working collaboratively together, optimizing, each one of them optimizing for trajectory and time. I would argue, next slide, please just click. Thank you. That's what we have now. If you look at a vehicle, it has inside it a huge brain, and that huge brain is optimizing for road conditions, for trajectory, for location awareness, lateral and longitudinal on the road at speed, relative to other vehicles and relative to its end objective. And let's have a look at some of these brains in operation. Next slide, please. Here is a sophisticated brain at work. Where you go? And there it is. Actually seen the car parked on the side of the road, just managed to miss it. Is this how we're going to implement autonomous vehicle AI? I think probably not. Let's go. Next slide. So there are three aspects, major aspects to vehicle location and timing. The timing and clocks inside vehicles, which essentially is a plethora of standards, many proprietary. We are looking in the industry to try to unify that with implementations like TSN, in-vehicle TSN, and so on. There are onboard sensors, which are being implemented by the autonomous and quasi-autonomous vehicle community, which give position and movement relative to neighbors to complement or replace GNSS information for absolute location. And then, of course, you have position, navigation, and time relative to a well-known reference clock, but that depends on satellite visibility and receiver integrity. And all these aspects, unfortunately, are not well linked, either vehicle to vehicle or in vehicle, and each takes significant computing effort. Next slide, please. Now, look, navigation actually is precise location and precise time, and autonomous driving will depend on the coordination of these to a common reference time, both inside and outside the vehicles. That's not there today, but what are the critical parameters? The relative location of a vehicle relative to adjacent vehicles, and then relative time, the time used by a vehicle relative to the time used by adjacent vehicles. Right now, there's no simple equation. We believe that we can solve this with sensors, and surely we have GNSS. Next slide, please. Unfortunately, there are well-known problems with GNSS. It's a very weak signal. It's not always available. There are tunnels, there are garages, there's urban canyons, skyscrapers. I think these are well-known statements now. And of course, you have jamming and spoofing, which is another additional, very, very common factor that's arising. So what are the solutions? Well, more sensors. We're going to put real-time maps with huge GPU requirements and intensive supplementary AI systems inside vehicles. That's going to make them much more expensive. We're going to deploy another layer of GNSS, a low Earth orbit, only a couple of 2,000 kilometers from the receivers instead of 20,000 kilometers from the receivers. Let's implement some kind of radio vehicle-to-vehicle dedicated short-range communications. And let's look at signals of opportunity. Surely, by putting all these together and synthesizing them, we have a solution. Can we have the next slide? Yeah. Unfortunately, in-vehicle sensors are not necessarily the solution either, and neither are signals of opportunity. If we look at the generic type of sensor that we find increasingly in quasi-autonomous vehicles and autonomous vehicles, we have radar, where there are problems of strobing and co-channel interference. As you add numbers of radars, with lots of radars all working around about the same frequencies, you're going to have serious problems of false positives. Map matching and LiDAR actually requires very precise location information, which relies, believe it or not, on GNSS. And unfortunately is subject to, right now, false positives in the locators, the base stations and the landmarks that are used for location. And cameras, we know, are inhibited by smoke, fog, precipitation, and IMUs can be engineered to be very, very good, but would be very expensive and are rapidly inaccurate over short distances. Generally, IMUs in drones, for example, rely on the constant GNSS visibility. And signals of opportunity, I won't go into any detail here, but there are obvious other issues with signals of opportunity. In particular, LEO has the same kind of visibility problems as GNSS. Just because it's nearer and the signal is stronger doesn't mean it can go through buildings. Okay, next. Next slide, please. Inside the vehicle, you have very low-cost oscillators, and quite rightly, because the vehicle manufacturers need their vehicles to be low cost. There's no reason to put rubidiums inside a vehicle, although Microchip would love that. There are many onboard timing requirements. There are up to 80 different networks inside a vehicle with that link different control entities, some more critical than others. Emergency braking, we would probably consider as critical. Do you really want emergency braking to be reliant on, for example, a tenuously visible GNSS signal? Probably not. And so, you know, the problem with this is that while it's hermetic, and if the vehicle timing is self-contained, the oscillator can drive the vehicle in it doesn't really matter if it's drifting around in time. When you have to coordinate between vehicles and have situational awareness, which is taking into account other vehicles as well as itself, then the oscillator drift and variation could be a serious problem. So let's carry on. Okay, so now I'm going to slow down. We get to a little bit of what we're the hub or the critical part of the presentation. Everybody understands what the urban canyon is. You have short-term visibility to GNSS or poor visibility to GNSS. If you're driving around with a nav inside New York, for example, you probably only see the GNSS about 20% of the time. Now, where does this timing signal come from? It comes from what we have devised as world time, which is a series of a canopy, if you like, of GNSS signals sitting high above the cities, high above the Earth, 20,000 kilometers, with a very weak signal that bathes the Earth. And we have these very cheap, low-cost receivers inside the vehicles that receive this signal. And we build from there a time scale. A time scale is essentially a coordination of satellite time, which is agreed by every country around the world and implements a global time. This is where we get our global time from. Can we go on, please, to the next one? Now, if we put a proxy layer of micro clocks within 15 to 30 meters of the vehicles, or let's say in a building at the corner of a building, so that the signal from these micro clocks, these proxy satellites or pseudolights, if you like, that are receiving a line of sight from the satellite system, so they do not get easily jammed, or they have visibility, continual line of sight to the global time, UTC. These clocks can now sit in a place where they can deliver a signal continuously to the vehicles below. Now, this looks very, very simple, but you have to realize that it's a huge simplification. The critical attributes of this kind of function is that the micro PNT must support not only an emulation of the radio navigation signal and the associated control plane messages, but these control plane messages are, if you like, ensembled and describe the position, the time, and the health of the clocking system, as well as handing out a GNSS signal. Now, this data is relatively static. So here we can say this is a chain of clocks. These could be on successive light posts, for example. If these chain of clocks can be ensembled as a micro cluster, then that cluster is essentially a replication of a timescale. It's a miniaturization of the global timescale down to, if you like, a city block. Can we go to the next slide? So here, for example, we can imagine a cluster or a group of clocks that are communicating between themselves. You can use very smart, resilient algorithms that leverage well-known clocking algorithms to mesh and cluster and ensemble the navigation and timing statements at that cluster. So now what you essentially have is, you know, what we were looking at in Martin's presentation, where you triangulate a UE. But here we're not triangulating a UE that may be moving at, you know, at any kind of speed. What we're doing is we're handing off extremely precise timing in order to give 1 to 2 centimeters in real time at any speed of situational awareness to the receiver. So the really interesting attributes here is that the micro PNT clock is now a miniaturization of the time scale. And that time scale can have any size because you can cluster the clocks using clustering algorithms that can be virtualized. Because these clocks are stable, you use pairwise matching between the clocks and build up an intelligence layer which knows exactly where all of the entities are in the system. So in other words, they're static, they're like an SBAS system, but miniaturized. So what we're really doing here is miniaturizing clocks that are extremely stable, that are extremely visible, and hand off PNT information extremely fast to very low cost receivers that have just a few nanoseconds of delay and continual visibility. Moreover, every vehicle is now tied to the UTC reference clocks. This means that intra-vehicles, a situational awareness of vehicle A, it knows that any vehicle that is its neighbor is also tied to that same time. Now you can begin to have inter-vehicle communication that has meshed UTC statements inside the vehicle rather than hermetic vehicles drifting around willy-nilly and wayward. So these clusters of clocks support effectively a distributed timescale, which is virtualized. Let's go on to the next slide, please. Now, having a look at these micro timescales, you can have them any size. If you have very challenging urban environment, you may have a small mesh, a small timescale, if you like, a dynamically configurable timescale based on static clocks that is understood by the vehicle as it moves across the city. It can move from mini cluster to mini cluster. It can move from a mini cluster to a macro cluster. And how would that work exactly if you have, say, a chain of clocks down the freeway? Don't your clocks drift? Well, we actually did some analysis of that and some mathematical models, which I don't present here. We're delighted to do that in the next presentation, where we modeled a chain of up to 100 consecutive clocks with picosecond level of noise dispersion between each clock, noise accumulation between each clock. And we found that up to a limit of about 100 clocks, we could maintain an extremely accurate holdover of the time between the chain of the clocks. So you don't only have to have a cluster, you can have a chain. It's unlikely, I feel, if you have these clocks every 300 or 500 meters, for example, this means you could have a 50-kilometer long chain with extremely low drift away from UTC. And it's unlike, I think the only place I was thinking of where you may have a 50 kilometers without a clock would be, for example, between Italy and France as you move through the tunnels.
Joe, yes, I have to ask you to come to the conclusions. Thank you.
Okay, that's it. So next slide, and that's it. So here we have the vehicles moving between the two, and one more, please. Next slide. This is just a statement of compared to the precise point positioning in other GNSS. Next slide. We deploy on lampposts close to the vehicles. Next slide. This is just a statement of the attributes of the PNT system. And finally, I'm going to just put one slide up and summarize. We have talked about quasi-autonomous vehicles needing timing. We know that the current solutions are inadequate. We need much tighter location and data much faster at lower cost. We need to engineer the Internet of Moving Things in micro timescales, just the same way that we have engineered a global timescale using satellite systems. Thank you very much indeed, everybody, and I apologize for the time.
Thank you, Joe. That was great. That was a really interesting topic, showing how synchronization is really impacting our, let's say, life. So we have a few minutes now for the final question and answer session. We received many very interesting questions. It's difficult to select, let's say, questions, and I'll try to pick a few ones, more significant. We'll see how to answer to the remaining ones. So I would maybe start with Anand. There was a question about your virtual stuff. So what work in the industry is happening to address the virtualized RAN, where the virtual DU and virtual CU are now operating on x86 processors to deal with terminating 1588 timing trails on these servers? Anand.
Thanks, Stefano. Okay, that's a great question. So the question, just to reiterate, was what work is being done on the virtualization specifically of the RAN, where some of this gear is running off-the-shelf x86 processors. So it's a good question because it's a combination of two separate aspects of my presentation from a while ago, which was to say, the architecture of the transport in the front and middle hall is evolving, and a lot of platforms are moving to disaggregated platforms. And there is actually a difference between a disaggregated platform that sits in the core or the edge of the network, because these platforms are white boxes that tend to use specific and targeted ASICs, custom, not necessarily custom, but off-the-shelf ASICs, but they are ASICs that do specific functions, including things like timing in 1588. Whereas when you get to the RAN, a lot of the virtualized platforms now would run off, as Stefanos and the question says, x86 processors. And how do they handle accurate timing and deterministic timing? Because, as we all know, x86 processors or whichever CPUs you're using and the cycles that run on them are anything but deterministic. So I think the approach to this is twofold. First of all, if you think about it, the RAN or the radio equipment itself has actually got some very tight timing requirements. From the control of the radio communications through to the actual RF on the antenna itself, there are requirements and timing, some as down as single-digit nanoseconds. We're talking about 1588 providing network-wide timing of tens of nanoseconds per node, or single-digit microseconds for the whole network, whereas the RAN itself has got even tighter timing requirements. The reason I'm saying that is because the whole community around working on virtual RAN, that includes people like ORAN, but also, of course, all of the vendors, and of course the key vendor of that CPU itself, the x86 vendor. They have been working for a while now to define not just protocol, but methodologies in the way the processes work and the coding and the cycles that run on them to add determinism to the processes, to enable these radio technologies to work and some of that communication to be accurate, as I say, between the control unit, the DU and the RRU, to be accurate to single-digit nanoseconds. So the work has been done initially by the vendors, then by the specifications written up by people like ORAN, and then as test vendors, we come in and we actually use 1588 packets to test the accuracy of these x86-based platforms to single-digit nanosecond. And that's not for 1588 timing initially, but just for the basic radio communication. So the work has been done by the vendors and the standards groups, and to enable radio communication to work to single-digit nanoseconds. That's the first step. The second step is then to, as I say, the 1588 part isn't really integrated into these virtualized RAN platforms yet. Most of the vRAN infrastructure and platforms that you see out there will still use direct GNSS connections, or the 1588 packet processing or the clock processing will happen outside of the vRAN systems. But but that's a future evolution of the vRAN platforms. But the point I will make is, if they have been designed and qualified to deliver nanoseconds precision for the radio comms, then adding 1588 stack is not a give me, it's not a slam dunk. but the infrastructure is there, and this is the result of work that's been done in the x86 community for years. The infrastructure is there to enable precision PTP timing to be recovered and transported in these virtualized RAN platforms. So apologies, that was a long answer, but there's a lot of work going on at the moment. The vRAN at the moment doesn't really do a lot of 1588 PTP yet, but it will come, and it's the platforms and the technologies and the developers are more than capable to support it.
Thank you, Ananda. Very, very clear and detailed answer. And there are many questions.
Stefano?
Yes.
I'd like to give an opposing view to this, if I may.
Yes. Yes, a short opposing view, Morten.
The radio interface does not require nanosecond accuracy. That's wrong. And I'm constantly telling the central unit developers they don't need time synchronization. Whatever you do, don't make yourself dependent on time synchronization in the centralized unit. It's the radio interface that requires time synchronization. The rest of the components, they only have to distribute time to the radio interface. And the centralized unit does not need to be time synchronized, and that will decrease the cost for this virtualized environment, removing the requirement for time sync in the CU. Thank you.
Thank you, Morten. Yes, indeed, the central unit is typically running on a server and doesn't require accurate sync. That was a good point. Okay, let's go to the next question. I think for Barry, there was a good question. So Barry, when you mentioned the GNSS outages, is there a planning factor for the length of the GNSS outages?
Yeah, Stefano, that is a good question. This is really heavy on the minds of all the network planning and engineering teams. Say, you know, if it's a short outage, you typically address that with a local holdover oscillator, and that can range from a low-cost quartz oscillator up to a premium rubidium oscillator that's going to hold 1.5 microseconds for 4 days. So that's the kind of range you have for local. Most of the networks now are engineered for backup across the network. So you let the local oscillator, if it loses its reference, it's going to lean on the network. And if you follow the standards and you use a good PTP flow with asymmetry compensation using APTS, you can really have an indefinite period of holdover if you've got a good quality, well-engineered network. And then the third one that we look at is really long-term outage, and that really speaks to the core clocks. And where the ITU has gone with that is to look at the enhanced PRTC, where you take your core reference clock and then discipline it with cesium. That will allow, and is specified to hold 100 nanoseconds for 14 days. So those are kind of the ranges. And I would say in summary, it's you always need to rely on a local clock for your holdover period, but then lean back on the network using the standards available today, and it's supported in all the equipment that the folks talked about here today to give you the long-term resilience and protection.
Thank you, Barry. So I saw many questions for Umut. Your talk were very popular. I just select one, Umut, for you. It was an interesting new topic. So could you elaborate on how the DTM technology is able to compensate the error on the network asymmetry?
Yes. Oh, okay. I'll try to explain it. Well, first of all, DTM applies the minimum time sampling algorithm. So what it effectively does is every 100,000 packets, when it traverses, it takes a sample. So in our case, we're using 25 megabits. So that's a lot of packets per second, what we take as a sample. And with this sample, we are aware of the latency. And these samples are taken so much, like I said, it's every 100,000 packets. If we would use 250 megabits, it would be much, much more. With this, because we now know what the every time that the latency is changing in the network, because we're actively, or DTM is actively monitoring it, we can drop the current jitter of the, well, actually the current jitter in the network, in the MPLS network in our case, we drop it to the 1000th percentile, so 0.1% of the actual jitter of the MPLS network. So the virtual circuit point-to-point is actually jitterless in this scenario. So on the other hand, because of we're doing this and we're measuring every 100,000 packets, also the asymmetry, we measure this both ways. So virtual circuit on DTM does this on both sides. So because of we're measuring it, a lot of times asymmetry immediately only adds more latency. Because we know now which way the latency is added, we can recalculate the PTP with this more effectively. And that is how it solves the asymmetry. We also use another algorithm, which is the minimum block sampling. And this is just in short, we also select the best block. Because we select the best block with the with the minimum latency, with the minimum asymmetry and everything, because when we choose the best block, this block will also have the best time. And that is why why this is so effective in transferring time long distances. I think that's that question. Yes. Is there more?
No, thank you, Umut. That okay. Was very good. That was very good. We are at the top of the hour. I would take the very last one to Joe, if Joe is able to answer in 1 minute. You try, okay. So how is it guaranteed that two vehicles in a class receive the time at the same time instant? They may experience different propagation delay between the transmitter and the receiver. Hence, they receive data information at different time instants.
Absolutely, they do, and that will continually change because they're pinging different clocks, and as they move between clusters of clocks, then they're addressing different clocks. But what I was trying to say was, essentially, you have a clustered clock, which is a time scale, and that time scale is a proxy UTC. So you have a miniature time scale, which is actually a reflection of UTC. So every vehicle is compensating continually hundreds of times a second to UTC. So it's actually generating itself in vehicle. The UTC time scale, if you like, is being replicated, or the UTC time is being replicated in the vehicle within extremely strict tolerances, because it's receiving that signal hundreds of times a second, probably over something like UWB, but it could be any type of RF. And because every vehicle has that awareness, now every vehicle is able to understand its lateral and longitudinal relationship to time, absolute time, therefore absolute location, and therefore to each other. I hope that's clear. And there's a lot behind this. I'd be delighted to handle questions offline.
Thank you, Joe, and thank you to be short, concise. So I think we have to wrap up, and we are at the end of, but I would like to give a couple of important announcements before we close. So first of all, a reminder that there are still two very interesting sessions that are going to be delivered. The one next Wednesday, 13th of May, about timing in finance, electric power and broadcast. And the very last one on the 20th of May on timing security, resilience, and GNSS issues. So I hope to see you all back. Then another important announcement in the next slide. By the way, you should register, as you know, at the web link you find there. So an important announcement is also that the face-to-face WSTS is planned in March 2021 in Denver, Colorado. It will actually be co-located with the NIEEE 2.2.1 meeting. So it will be very interesting to see how we could also have some joint session with the IEEE group. And you find more information at the website you can see here. And finally, I just would like to thank you for attending today. The slides and the recording of today's presentations will be emailed to all the registered attendees. And again, thank you and have a great day. Bye.
Thank you, Stefano. Thank you, everybody.
Well, thank you very, very much for this.